Hi, this is Suchitra Sebastian. This is our quantum materials laboratory in the Maxwell Center Cavendish Laboratory. So the conception of our lab started over 5 years ago when the Maxwell Center came into existence. And we were in the very fortunate position of being able to design our lab from the ground up. So this lab has been a long time in the making, but finally, just a few months ago, the culmination, as it were, of the laboratory came into place with one of the very few pieces of equipment in the world that is able to reach 22 Tesla. So that is a very, very high magnetic field, more than 10,000 times the size of a fridge magnet, and going down to about 10 millikelvin. And that is very, very close to absolute zero. And this piece of equipment, such a strong magnetic field and such low temperatures, are available maybe 1 or 2 other places in the entire world, and definitely not in the UK. And so it had to be custom made for us. The lab has been waiting for this equipment to arrive, but it just got here a few months ago, and in some ways it is the culmination of the design process, but also the culmination of a series of processes and lab elements that go together toward the measurement process in very high magnetic fields and very low temperatures. And a slightly unusual aspect of lab, which you might be able to see here, is that we've created a sort of arboretum that conjoins this world's largest magnet that's in our lab. And I think it's always been about the human element of the lab and the aspect of the lab that is alive in some sense. So our lab is actually one of the very few to integrate all the steps right from material synthesis. The materials that we study in our laboratory start right at the material synthesis stage, and then we study it. We especially study it under extreme conditions, which I'll talk about in a bit. What I find most fascinating about these materials that we study is that they're living, jostling collectives of electrons. So in a single milligram of material, there are a trillion electrons. So that's kind of hard to imagine. That's as many stars as in the observable universe, that many electrons in a single milligram of material. And so when we are working with this, our philosophy is very discovery oriented. Our entire approach is to try and discover new phases of matter. So like, say, water, ice, steam. So those are phases of matter you're familiar with. It's the same constituents, but organized differently. In the same way, these trillions of electrons organize themselves differently, collectively organize themselves differently. And our role in the laboratory is to try and create conditions for them to collectively organize into an interesting, novel form of matter, a novel form of quantum matter. At the moment, one has to cool down these materials to low enough temperatures, about, say, minus 100 degrees, in order for these electrons to form this collective quantum wave. So what we're trying to do is to understand a little bit better what are the conditions necessary to create superconductors? How do we create new superconducting materials that operate under higher temperatures that will be more practicable? So already superconductors are used for really big magnets. They can be used in elements of power grids, so example, fault limiters. They can be used in electrical motors that are very, very light for electrical aircraft, for wind turbines actually, that are much lighter than the conventional motors. But for instance, in order for them to be laid as electrical cables that go over long distances, it'll be even more applicable if we can use them at higher temperatures. And so this kind of research that looks into unconventional forms of matter spans the gamut from technologies that are already usable. So superconducting technology, for instance, is already something that's in use. LED panels, for example, all of these are already in use, but Making them better is one of the ways in which this research to understand how electrons collectively come together can be used, right to the other end of discovering new fundamental exotic forms of matter, which we don't as yet know how they're going to behave. But once we discover them, then that is part of the pipeline of them ultimately reaching applications which will transform everyday life.